Well, hi everybody, howdy. Mike here, and we're back for another edition of Lewis Structures. And like we said last time, we're going to start off with another example of a polyatomic ion. So I'm going to go a little fast. If I lose you, you should probably go back and watch part 2, all right? So here we go. What's the Lewis structure of carbonate, by the way? That's a very common polyatomic ion. And so here we go. Who's going to go in the center? Carbon. It's got the smallest electronegativity. Add up valence electrons. 4 valence electrons for the 1 carbon. We've got 3 oxygens at 6 each. 18 electrons. Things are looking pretty good. We got an even number of electrons. Don't forget this. Charge. We got a -2 charge. That means you add 2 electrons. So we're playing with a total of 24 electrons here. And let's go and make the minimum number of bonds that we can. C, O, O, O. 1, 2, 3. Take away 6 electrons. That gives us 18 electrons. We will find out that that ain't gonna work. Each oxygen requires 6 more electrons to have 8. This carbon needs 2, so we need 20 electrons, and we only got 18. So we're gonna have to make another bond. If you notice, you get good at this, you'll notice, hey, I'm 2 electrons short, just 1 more bond goes in there. Uh-oh, double bond, where's it go? Which part? It don't matter. We'll talk about that later. But what does matter is you take away and deduct your 2 electrons, and we should be able to place all of them. 4, 6, 8, 10, 12, 14, 16. And for now, you can make a little bracket around it and put a -2. But what's probably really plaguing you right now is like, where's the -2? Which atom is it on? And so we have a tool. The tool is called formal charge. Sounds like something the district attorney gives you, huh? But anyhow, what formal charge is a way of testing each atom to find out whether it's basically overlent or underlent the number of electrons it usually would do. So for example, usually oxygen has 2 half-filled p orbitals, and it'll make 2 bonds. But if you stick an electron on there, it'll make less bonds, and that makes a -1 charge. So what we're going to do is we're going to do this test to each atom in the Lewis structure. And if there's equivalently bonded atoms, you only have to do it once. So you take the number of valence electrons that each atom had when it went into the molecule, and then you take a look at it while it's in the molecule and it's bonding, and you take the number of non-bonding electrons and you subtract that. And then you take 1/2 the number of bonding electrons, and we're going to do that for every atom in this carbonate structure. All right, so back to this. What we're going to do is we're going to test carbon's formal charge. Now, I have to treat these 2 oxygens differently. So this is going to be carbon. We'll do that. Then what I'm going to do is I'm going to call this double bonded O. And then single bonded O. And we're going to go and look at the structure, and we're going to do the formal charge test on everything. Okay, so here we go. Carbon, 4 valence electrons minus the number of non-bonding electrons. Those are the pairs. I got none. Minus 1/2 the number of bonding electrons. Bonding electrons are the dashes. 2, 4, 6, 8. 4 minus 0 minus 1/2 of 8. Where I come from, that is 0. So the actual charge on that carbon atom is 0. All right? which means the negative 2's got to be coming from somewhere else. Okay, cool. Let's do the same thing with this oxygen right there. Oxygen, 6 valence electrons, minus the number of non-bonding electrons, 2, 4. 6 minus 4, minus 1/2 the number of bonding electrons, 2, 4. 6 minus 4 minus 1/2 of 4, and once again that's 0. The mystery here is unraveling. Where's that negative 2 come from? Well, both of these are equivalently bonded. Seems to me that if there's a negative 2 charge, each oxygen should have a negative 1. So let's go ahead and see if that's true. Looking at either one of these, don't have to do it over again because they're both equivalent. 6 valence electrons is what oxygen has, minus 6, 2, 4, 6, minus 1/2 of 2, 6 minus 6 minus 1, minus 1. So the negative 2 charge on carbonate comes from each singly bonded oxygen. And it doesn't even matter what molecule it is in, folks. If you single bond an oxygen, it's always going to have a formal charge of negative 1. So maybe you've seen this guy, hydroxide ion. Remember back to acid-base world? And you'll find out if you do a formal charge on that hydrogen, then that's going to be a 0. 2 minus 2, and there it is, single bonded oxygen. That's where the negative charge on hydroxide comes from. And so you should be able to do this in any Lewis structure, whether it has a charge or not, actually. So let's whip through another one real quick, and then we'll move on to something else. Alrighty, I thought it would be a cute idea to take the ammonium ion. That's a little bit different, right? So let's whip through the Lewis structure of it. Obviously, nitrogen's going to go in the middle because hydrogen can never go in the middle. So we've got a nitrogen contributing 5 valence electrons. We've got 4 hydrogens, each contributing 1, so 4 valence electrons. And by the way, if you stop right there, you're going to be in a world of hurt, because a lot of times when you have an odd number of electrons, that ain't going to work out Lewis structure wise. You're going to have to end up having something that's either wrong or it's just not as stable as it could be. But look, we're forgetting that positive 1. We're forgetting the step where we factor in the charge. Now, watch out. People always think electrons, you know, when they see a plus, it means something was added. But here I have to deduct 1 electron. Think like a sodium or something. When that's a positive 1, it's because it's lost an electron. So really here what we've got is a total of 8 valence electrons. All right? Let's go ahead and lay them out in space. Let's make the minimum number of bonds that we have to. And you know what? We just used up all of our valence electrons right there. Pretty simple. Where's that positive 1 come from? Well, let's do a formal charge test on everything. All right, let's go. And I only have to do it twice because I have to just do it for the nitrogen and the hydrogen. So we'll do nitrogen. Number of valence electrons in nitrogen and everything in group 5 is 5. Minus the number of non-bonding electrons is 0. All right, minus 1/2 the number of bonding electrons, 2, 4, 6, 8. 5 electrons minus 0 minus 1/2 of 8 is 4. That's a plus 1. So that charge is right there. If I was a risk taker, I could just say I'm done. But you know what, just to over-explain, if anything, I'll do hydrogen. Duh. That's a risk when you count wrong. 1 electrons minus 0 non-bonding electrons minus 1/2 of 2, 0. So whenever you single bond a hydrogen, it ends up having a charge of 0. All right? And when you actually make nitrogen overland, usually nitrogen has 3 half-filled p orbitals, and it would be able to make just 3 bonds. But when you force an atom out of its sort of comfort zone from the periodic table, that's when you get formal charges to occur, and that's why we have polyatomic ions. I mean, it's kind of funny. It's not unstable. It obeys the octet rule, but it's just doing what it normally wouldn't in overlending, kind of going into oxygen debt or something crazy like that. Sounds like the shadow banking system. Okay, I got another little pattern that we're going to talk about next. Okay, folks, so we know about the octet rule, and it's really important, right? Well, there's another sort of rule of thumb, if you will, that determines which structure you can come up with is going to be the most stable. And that is the structure you can come up with that has the fewest formal charges is the one that's most stable. So I'm going to give you an example. What if I go do carbon dioxide? I'll let you go do the steps. You'll find out that when you add up all the valence electrons, you're going to be 2 pairs of electrons short, and you need to make 2 additional bonds. But what if you were feeling creative and you wanted to do that? Well, according to everything we've talked about so far, they'd look like they're equivalent structures. Like I could just, hey, make a triple bond over there on the left and a single bond, and everything has got 8 valence electrons. But if you do the formal charge test, like we did, double bonded oxygen, 0. Carbon bonded 4 times, 0. Another double bonded oxygen, 0. But if you do that over here, you're going to find out that's a -1. That's a +1. So this one is more stable. All right. Now here's a, whoops. So that one is more stable. Now we have another term for these things. They're viable structures, just one's more stable than the other. We call these things resonance structures. This happens a lot with multiple bonds. So it is theorized, and you folks who are going to go further on into organic chemistry, you're going to have plenty of resonance structures thrown at you. But it's theorized that these sort of add stability. They give the electrons sort of room to roam, if you will, and this adds stability if there are resonance structures possible. They do this funny kind of sort of thing where what they do is they make double arrows between the structures. So for example, you can come up with 3 resonance structures of carbon dioxide, and they'll do this. And that's not really meant to be flashing back and forth. It's just meant to be a symbol of, you know, that's another possible structure. And then you do another double arrow here, where you could put a triple bond there. So if this turns you on, you're going to like organic chemistry, because this is called resonance stability. The more resonance structures you have, the more stable the molecule is. So just, and then you know what? They say that an average of what happens is what the real structure is. So if you were to go back in time when we talked about carbonate, right? You take a carbonate, you know, I forgot where we put the double bond, but you could have put it in any of the 3 places. But you have 3 possible resonance structures that exist. I could have put the double bond over here, and that would be another resonance structure. So it didn't even really change how many bonds or what type of bonds, but you have different possibilities as to where that double bond could go. And so that's just a kind of a very Star Wars-y kind of thought, but this is going to blow your mind too. The actual structure is considered to be an average of all the possible resonance structures. Now with CO2, you'd have an average of 2 bonds on each side, but the carbon-oxygen bond in carbonate is sort of like 4/3 of a bond. And so, yeah, it's brain-twisting stuff. So, I want to leave you with one more thought about what we're going to talk about next time. All right? Next time, we're going to talk about what shapes our molecules in 3 dimensions. So I'm going to give you one name of a theory where we're going to start next time, and we'll pick it up there. All right, folks. Next time, we're going to talk about what they call Vesper. Valence shell electron pair repulsion. Actually, if you said it like it looks, it'd be like VSEPR, VSEPR. But that doesn't sound as cool as Vesper. And that is the idea that these molecules are not all the way we write them on paper. So if you take something like ammonium ion, you say, hey, it looks like, you know, kind of like shaped like a cross. But what happens is all these things surrounding a central atom act like blobs of negative, and they repel, and they want to, even though they're tied together, tethered together, they want to get as far away from each other as possible because they repel. So what happens is this thing is actually shaped like that. That's 109.5 degrees apart from each other, and that's further apart than 90 on paper. So bring the 3-dimensional part of your brain next time. Well, everybody has a 3-dimensional brain, but bring the part that can think about 3 dimensions good. Next time, we'll talk about the shapes of molecules. Cheerio! Captain Crunch. Fruity Pebbles. Bye.